is a sequence. It is a recursive sequence. And a1 is 2. We can write it like this. And an plus 1, an to the power of n plus 1 minus, right?
Yeah.
Okay, then it says for each integer n greater than or equal 1, suppose that p is greater than 2 is prime. So because p is greater than 2 and is prime means p is what?
Means p is greater than or equal to 3.
Yes, or p is odd, right?
Yeah.
And k is a positive integer. Then it says prove that some terms of an is divisible by p to the k. Okay. Now for starting a problem, especially in full solution exams like AMO, JMO, IMO, the most useful idea is what? In prom is also useful, in SUMaC useful. The most useful idea in all these exams, important exams, is
Small cases.
yes, small exam. We can find the idea by considering a small exam, okay?
Yeah.
And in all years of JMO, IMO, meaning design, and it helps us to reach the solution faster. So here there are lots of variables. We can use a small example on what?
On p.
Exactly. So the first p that we should check is what?
3.
3. And now let's consider power of 3. 3 to the 1, 3 squared, okay? So first 3 to the 1. It says prove that there exists an element that is multiple of 3. So how can we prove this? Try this one is not hard. Try to find what is multiple of 3, okay?
Okay. Okay.
One team toward
I
3.
think after at least 2 n steps, then 3 to the n will be divisible. But less than that, at least after that.
Can you say it again?
After 2n, a of 2n, well, 3 to the n will divide a of 2n.
You prove 3 to the n divides a of 2n?
Yeah.
Okay, can you explain?
Because we first have a of 2 equals 0 mod 3, okay?
Okay, so let's check this one quickly. So grade 1 is 2, next one is what? 2. A2 is 2 squared minus 1, which is 3, right?
Yeah.
Next one is 3
That's 0
cubed
mod 3.
minus 1, right?
Yeah.
So this
So
one
we
is
can
2,
call
this
this
one is 0,
20.
this one is 2 again, not 3, right?
Yeah.
And you can say what? You can say
let's say
next
we
one
get
because
something.
it is negative 1, right?
Yeah. We say the next one is also 0.
Negative 1 to the power of even minus 1, right? Which is 0 again.
Yeah.
Next one is 0 to the power of something. It's not important. 0 to the power of k minus 1 is negative 1. So it would be negative 1, 0, negative 1, 0 alternatively. So then what?
Then I said, okay. So, let's just say, like, if we go by this, so on a of 2, we have 0 mod 3, that's equivalent to 0 mod 3. That means a of 3 will be equivalent of 0 mod 9 minus 1. Because you're at least doing this like squared. So this is equal to minus 1 mod 9. then we get A of 4 will equal to 0 mod 9. Then we can do the same thing over and over, and we get like A of 6 will be equal to 0.
Okay. I understood you want to say. You proved, you said A2 is 0 mod 3, right?
Yes.
And then you said you consider A of 3 mod what?
Mod 9.
Mod 9. Okay, so how you calculate A3 mod 9? Because you
So
say
I
it
said
is 0, 0, it is to the power of 3, right?
yeah.
So
So
it
you
is
know it's
mod
at
mod
least gonna
9
be
is
0 mod
negative
9.
1. Yes, I agree. Then you
Yeah.
consider A4 mod what?
9 still.
Okay. A4 mod 9. It's negative 1. So A4 mod 9 is 0, right?
Yes.
So because it is multiple of 9, then you reach the power, so you can say A5 mod what?
Then we get A5 mod 27.
Exactly. Again, you can say it's negative 1, and then A6 mod 27 is 0, right?
Yes.
And so on. So you can say 3 to the power of n divides A2n, right?
Yeah.
Okay, or let's use m because we have n. My approach is not similar to your approach. I solved this previous time, I think 1 month, 2 months ago. But let me tell you, because we have this form, I try to use LTE, okay? And I saw it is something to the power of something. So I said if I want to find V3 of, for example, an plus 1, it is equal to V3 of an to the n plus 1 minus 1, right?
Yeah.
So we should have something. 3 shouldn't divide an, 3 shouldn't divide 1. 3 should divide an minus 1. But our problem here is that these are 2, right? And we can't have this condition, agree?
Yeah.
So what should we do to reach to something to be able to use this? Is A1, A2, A3, A4, A5, 2, 0, 2. So, okay. So look, if you want to use for an should be this part, right? Because 0 is not possible. An shouldn't be multiple of 3, so we should use ans for these things too. But our problem is this one. 3 doesn't divide an minus 1, so it would be bad, right?
Yeah.
But we had this problem also in AIME. We should do something to be able to use that. So we should do what? Understood what I said?
No, not really. Can you repeat?
So from what part you couldn't understand? I said I want to use LT, okay? So because I want to use LT, I want that these conditions should be satisfied. So here n should be what? For which n's we can say 3 doesn't divide an.
I don't understand.
N should be what? Because 3 doesn't divide an.
N should be 2n. 2k.
A2k's are multiple of 3. We said 3 that shouldn't divide.
Oh, 2k plus 1.
2k. Okay, pay attention because look, these problems are not easy at all. Okay, pay attention to understand. Okay,
No, I am.
completely. Oh, great. So n is 2k plus 1. Now I want to use this. So I say, okay, from here, I consider V3 of A2k plus 2 is equal to V3 of A2k plus 1 to the power of 2k plus 2 minus 1, right? Then we know 3 doesn't divide A2k plus 1, and that's good. 3 doesn't divide 1, but 3 shouldn't divide A2k plus 1. 3 should divide A2k plus 1 minus 1. This condition is satisfied. Does this condition satisfy or not? Satisfied or not?
No, it does not.
Okay. So we should do what?
We should square the terms.
Exactly. We know a2k plus 1 is -1 mod 3, right?
Yes.
So if we raise it to the power of 2, it is 1 mod 3, right?
Yeah.
Okay, so let's use like that. V3 of a2k plus 2 is equal to V3 of a2k plus 1, the power of 2k plus 2 minus 1. Then we consider this one as a2k plus 1. As we said, the squared, the k plus 1 minus 1, right? Now we can use LTE because 3 doesn't divide a2k plus 1 squared. 3 doesn't divide 1, and 3 divides a2k plus 1 squared minus 1, right? All these conditions are satisfied.
Yes.
And also 3 is an odd prime. So then by LTE we can conclude what?
By LT, you can include that this is equal to V3 of k plus 1 plus V3 of a to the 2k
V3
plus
of
1
k
squared minus
plus 1 plus V3 of what?
a to the 2k plus 1 squared minus 1.
Yes. And let me tell you something. It's better to not use k because it says we have k, okay? So if you want to write, let's consider this one, or let's consider k. K prime, 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 k prime. Okay, k prime and k prime and k prime. So we want that this one be at least what?
We want this to be at least 3 to the k.
Yes, we want that this
At
one be
least k, at
multiple
least
of
k, at least
3k.
k.
So this one V3 of that should be at least what?
K plus 1.
At least k, right?
Oh yeah, no. Yeah.
Because it
Okay.
says we should prove that it is multiple pk, always for all k's. So how can
Okay.
we make sure that this one is at least k?
We can just set k prime to equal to v k prime plus 1 equals 3 to the k.
K prime
3 to the
plus
k
1, 3 to the k, so 3 to the k minus 1.
minus 1. Yes.
So for this number, we can say V3 of a2k prime plus 2 is at least k, right?
Yes.
Okay, so it says we want to find only one term that is multiple of that. Let's see. Prove that some term of the sequence. Okay. And also by this way, we prove there are infinitely many terms that are multiple of 3 to the k, right? Because k prime can be any number, right? Because k can be any number. Look, k, 1, 2. And you can also say this 3 to the k minus 1 times q, right? Or times t. Do you agree there are infinitely many good k primes? Let me fix on side. Because k prime plus 1, 3 to the k t minus 1. Do you agree if k prime is this?
Yeah.
So k prime plus 1 is multiple of 3 to the k. So, and because we can have t can be any number, there are infinitely many good numbers, right? For p to the k. Okay?
Yeah.
Okay. Now this one was for 3. In next step, we should consider p what?
P equals 5.
Exactly. P equals 5, and we said an plus 1 is an. Let's write it again. An plus 1 is an to the n plus 1 minus 1, and a1 is 2. And now for p5, you want to prove that for each 5 to the k, there exists some good term, right?
Yes.
Like 3. So try this one first on your own.
Okay.
One hint for 5 to the k.
Yeah, can I have a hint?
Okay, so we want to solve it like 3 that we saw here. So we should do what first?
We should first see when it's 0 mod 5.
Yes, we should consider mod 5. So if we consider mod 5, A1 is 2 mod 5. A2 is
Yeah.
what mod 5?
3 mod 5.
Yeah, 2 squared minus 1 is equal to 3 mod 5. A3 is what mod 5?
1 mod 5. A4
Is
is
what?
0 mod 5. 1.
3 cubed minus 1, 26. 1 mod 5, right?
Yes.
A4 is what mod 5?
0 mod 5.
1 to the 4. Constant mod 5. 1 to the 4 minus 1, which is 0, 0 mod 5. A5 is what?
A5 is 4 mod 5.
Yeah, so negative 1. A6 is what mod 5?
A6 is 3 mod 5.
Is what?
3.
Pay attention.
Oh, it's 0.
Exactly, it's 0. Because negative 1 to the power of 6 is even, minus
Yeah.
1, 0, right?
Okay, that's 26. Okay.
Okay. A7 is what?
A7 is then going to be again negative 1.
A8 is what?
0.
Yeah, so from here we have negative 1, 0 from here. 0, negative 1, 0, negative 1, so on. Want to try the rest on your own or want more hints?
More.
You said more hints, right?
Yeah.
You said, okay. So now that we want to prove, we want to solve exactly like this problem. So we should consider V5 of which AIs.
Mm-hmm. What do you mean?
So now we want to prove what? First, our
We want to
goal
prove
is what?
that you can get V5 of like A of n is equal to, I don't know, 5 to the n prime.
V5 of
5
A
to
to
the
the
n prime.
is at least k, right? We want to prove something like this,
Yeah.
right?
Yeah.
So then we should focus on which a's. A what numbers?
0 mod 2 greater than or equal to 6. Greater than or equal to 4.
So n should be what numbers?
Greater than 4, 0 mod 2.
Yes. So we can write it in what form?
0 mod 2.
So we want to write it n, for example,
4
2q.
plus 0 mod
Okay.
2. 2q plus 4.
Yes, but we can say 2q and q is at least, for example, 2. Okay.
Oh,
Q
okay.
is at least 3.
Okay.
Okay, because we want to find one element. One element also is enough. So if you find one element, we don't need to consider small cases, right?
Yeah.
So V5 of this, A2Q is what?
A2q is equal to no, it's obviously equal to 3. No, 0, 0.
No, look, A2Q is equal to what? Not mod
Oh.
something. It's equal to what?
V5 of A2. Wait, 1 second. I don't know, what is it?
The problem says it is a recursive sequence, and the problem says recursive
So
sequence is
it's
what? And all
A2q minus 1
exactly. The power of
to the power of 2q
then.
minus 1.
Okay. Now for which q it is at least k? Should do what here?
Q equals 0, 1, 2. Oh, wait, no. Q
Look, we want to prove this. It is not guessing. We don't want to only be at least one multiple of 5. We want that this one at least k.
Yeah.
So then we should do what?
We should say this is equal to we can call this a to the 2q minus 1 squared to the power of q minus 1 to the power of q.
Yeah, but we want to use LT for this, right?
Yeah, so you can do a to the 2q minus 1 squared.
Exactly.
The whole thing to the power of q.
Whole things to the power of q minus 1. And why LT conditions are satisfied here?
Because 2q minus 1 is squared is equal to 1 mod 5, so it does not divide. 1 equals 1 mod 5, and 1 minus 1 equals 0 mod 5. So everything checks out.
5 doesn't divide this, 5 doesn't divide 1. But 5 divides a2q minus 1 squared minus 1, right? And we said q is at least, because we want to start from here, let's consider q is at least 3, okay? Because we have this period -1, 0 from here. Okay, so q is at least 3. Now, if you use LT, this one is what?
This one is equal to a to the 2q minus 1 v5 of a to the 2q minus 1
squared minus 1 plus?
Yeah, minus 1 plus v5 of q.
Yes, now we want to do something to reach greater than equal q, so.
Yeah, so you can just call q is equivalent to 5 to the power of k.
5 to the power of k, for example, times t, right? Then a times 2q, then 5 to the k divides a to q, right?
Yes.
Okay, 3 and 5, I remember, if you want to generalize this approach, it would be a bit hard. But I remember 3 and 5 were similar, 7 or 11. One of them was different. And if you use that, then you can generalize. So we check P3, P5, and P3 and P5 were completely similar. Agreed?
Yes.
Okay, now let's check P7. Try to see, can you use same approach for P7? Try first on your own, okay?
Okay. No, can I have a hint?
This one is a bit different from P3 and 5, agreed?
Yes.
Okay, so if I consider A1, A1 is 2, mod 7. A2 is what, mod 7?
A2 is equal to 3 mod 7.
Exactly. A3 is what, mod 7?
5 mod 7. Or -2 mod 7.
27 minus 1, 26? Yes, or -2, right? A4 is what, mod 7?
A4 is 1 mod 7.
Yes. A5 is what, mod 7?
0 mod 7.
A6 is what?
-1 mod 7.
A7 is what?
-2 mod 7.
Yes. In all previous parts, when we reached -1, because it was in this -1 was in A odd, and A even we had -1, 0, -. But here, this approach didn't happen, right?
Yes.
So A8 is what?
1 mod 7. Oh, no. A8 is... Yeah, 1 mod 7.
-2 to the 8 minus 1. Or we can do something. We can say it's 2 to the 8, right? Or it is 8 times 8 times 4 minus 1. So it's 1, 1, 4 minus 1, 3, right? So we've not found a good pattern so far. A9 is what?
A9 equals 3 to the 9 minus 1 mod 7.
Exactly. Mod 7, it is what?
I have no clue.
You said A9 is what, mod 7? Have you
I
calculated?
don't know.
Okay, so calculated A9 is what, mod 7?
Calculated. A9. Okay. Yeah, it's 5.7.
5, you said?
Yes.
Okay, so 3 squared is 9. 9 to the 4 is 2 to the 4. Times 3 minus 1. 2 to the 4 is 16. 6 minus 1, 5. So still we don't have a good pattern. Let's write also this one. We can say 5. A3 is 5 or negative 2. And okay, so let's write also this negative 2 as 5. So do we have a good pattern? Not yet. A10 is what?
A10 is equal to 1.
It's 1. Okay, let's check. It is 5 or negative 2 to the 10 minus 1, right? Negative 2
Yeah.
to the 10 is what? Is, you can say 8 times 8 times 8 times 2, right? 3
Yeah.
times 3, 9 minus 1. All of them 1, 2 minus 1, 1. Exact. A11, so is what it is.
A11 is not equal to 0.
0. A12 is what?
So now we've reached it. Oh, no, we've not. Never mind. It's negative 1.
Negative 1. A13 is what?
I'm gonna guess 5. Yeah, it is 5.
5. So we can guess that the period is what and from which element?
We can guess that the period is 6.
From what element?
5 through 10.
Yes, 2, 5. Look, 2, 3. We don't have. But we have 5, 1, 0, negative 1.
Oh, never mind.
But here it's not good. If you
3,
consider
2.
from 1, 0, negative 1, this. So from here is good, right?
Yeah.
And A14. Okay, now let's check until, because the length is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So we should check A14 and A15 first to make sure. A14 is what?
A14 will be equal to 3.
It's 3. Have you calculated this?
No, I'll do it now.
Yes, we want to check that 3, 5 satisfied, then we try to prove, okay? So first calculate this.
Yeah. It is 3.
It is 3. Okay, so look, you should calculate 5 to the 14 minus 1, right? Or negative 2 to the 14 or 2 to the 14 minus 1. Again, it's 8, 8, 3, 4, 12 times 4 minus 1. It's 4 minus 1, 3. A15 is what calculate last time. A15.
Mm-hmm.
Okay, calculate A15.
Yeah, I'm getting 5.
It's 5. Okay, let's check. A15. 3 to the 15 minus 1. So 3 squared is 9. It's 9 to the 7 times 3 minus 1. 9 is what? Is 2 to the 7 times 3 minus 1. 2, it is 8 squared times 6 minus 1. It is minus 1 minus 1 minus 2, which is 5, right? Okay, now
Mm-hmm.
first we want to focus on this. We want to focus on this part, that this period will happen forever, okay? For this one, we tried this problem, a small example we used, and then I told you try the rest. And I think last session we finished that. Oh, no, we've not finished that. I told you review our previous session, and okay. So we wanted to solve it for P7 and then generalize it. Have you tried the rest of this problem?
No.
Look, it is so much important to try these things because I think here we worked on this. I told you try the rest. Previous session you didn't try the rest, and also this session you've not tried the rest. Why?
I had a job last week.
You didn't have free time to work on the homework?
No.
Okay. Look, it took around 1 hour. You didn't have 1 hour to complete these?
Yeah, I should have done it. I'm sorry.
Okay. Because look, it is so much important. We tried these, we worked on all cases, and then we checked P7, only one part. For example, if you try and you couldn't, that's okay. Then we can work on the rest. But so let's finish this one because it is the second session. You've not tried this. Okay, so it was problem 3. So let's review this. A1, AN plus 1 was this. So let me copy this one and finish this problem. Okay. Now, A1 is 2. AN plus 1 is AN to the n plus 1 minus 1, right? And it says for each P prime and K that is a positive integer, prove that some term of the sequence AN is divisible by P to the K. So, do you remember our approach was what for solving this problem?
No.
You use a small example. You remember we used a small example?
Oh, yeah, yes.
We use a small example on what?
On what n is?
On P. Look, and then we solved P3, we solved P5, and then P7. So try again for P3. Try to solve the problem for P3 again. Okay.
Okay.
Okay. What have you done for this part?
I realized that it cycles mod 3, like 2, 0, 2, 0, 2, like that. I'm trying to use lifting the exponent, but you need a of n to equal 1 mod 3 to use that. So,
A1, A2 is 2 squared, 4 minus 1, 0. A3, 0 cubed minus 1 is -1. Or 2, then A4 is 0, A5, -1. And then what?
A6, 0.
Yes, A6, 0. Then we should do what?
Go to mod 9.
Yes, you should prove that for any k, that 3k divides at least one element here, right? Okay, could you find which element is multiple 3 to the k or not yet?
Not yet.
Okay, one hint for this part or wanna keep trying?
I'll keep trying.
Okay, sure.
I think it might just be 2k.
3 to the k divides a what?
2k.
2k. Why?
That's what I believe.
Yeah, but you should prove it. So, how could you prove it or not?
I'll try to prove it.
You couldn't prove it?
I'll try it.
Okay.
I think I proved it.
Can you explain?
Yeah, so we know that, I'm just going to use induction on it. and say that so first we assume the 2kth term equals 0 mod 3k to the k.
Okay, so look, when you say 2k, let me change this k to because this k for this one, let's change it to m, okay? Because k cannot be equal to 0. So you say m should be 0
No,
mod
I am counting.
3 to the k, right?
I'm sorry?
Look, you cannot say k should be 0 mod 3 to the k, because k is not multiple of this. So we should change this. You can say yes, we can select an m that is 0 mod 3 to the what?
It is k, it's not m.
So k cannot be 0 mod 3 to the k.
I know, a of 2k can be.
Look, a of 2k also is not multiple of 3 to the k. Look, this k shouldn't be related to it shouldn't be exactly same as this one. Let me show you why. Understood what I mean, or want me to explain more?
No,
Okay, so
I'm
let me
proving
tell
by
you.
induction.
Look, A2. Okay, so let's check. You say that 3k divides to A2k, right? Okay, then what?
Then I first have my base case, where k is 1, and that works.
For k1, 3 to the 1 divides A2, yes. Then what?
Then I say, okay, so, yeah. So now, what is a of 2k plus 1 mod 3 to the k plus 1? So, because it's going to be minus 1 mod 3 to the k plus 1.
You said a of 2k plus, you are calculating a of 2k plus 1?
Yeah, equals minus 1 mod 3 to the k plus 1.
Okay, let me check. It's A2k to the 2k plus 1 minus 1. You said it is minus 1 mod, because you said 3 to the k. You want to cancel k, correct? K plus 1. You said 3 to the k divides this. So because we raised the power of something, so you said mod 3 to the what is negative 1, 3 to
K
the
plus
k
1.
plus, yes, exactly. Then what?
Then we say, okay, and then a to the 2k plus 2 is then going to be equal to minus 1 to the 2k plus 2 minus 1.
Yes.
Mod k, which is equal to 0 mod k.
Exactly. Our solution was not this one, it's solved, but good job, it is correct. Mod 3 to the k plus 1. Okay, because you cannot generalize it for example, other primes, but that's correct. Now we should check what in the next step.
Where p is 5.
5, exactly. We check P5. P5 and 3 are easy. P7 will be a bit harder, and with P7 we can solve for general P. So let's solve P5. Try P5 first on your own.
Okay. 5 to the k is divisible by a to the 2k plus 2.
5 to the k is divides a 2k plus 2. You said this?
Yes.
Okay, so let's check. Again, if we consider mod 5, a1 we know is 2, right?
Yeah.
A2 is 2 squared minus 1, which is what?
3.
A3 is 3 cubed minus 1, which is what?
26. So 1.
26, 1. A4 is 1 to the 4 minus 1, which is what?
0.
A5 is 0 to the 5 minus 1, which is what?
Minus 1 mod 5 squared.
Yes. If we consider all of them mod 5, then A6 is what? Negative 1 to the 6 minus 1, 0, right? So if we consider mod 5. Okay, so can you explain how you prove this again by induction?
Yeah, exact same method as last time.
Exactly. Okay, so P5. Now for P7, we cannot use similar thing, and in this point we try. Maybe from here we can reach another solution. So try to check P7 on your own first, okay?
Alright.
One hint or wanna keep trying?
Can I have a hint?
Okay, sure. For this one, previous approach doesn't work, right?
Yeah.
Okay, so at first we should consider it mod 7. So if you write A1, A4, A5, A1 is 2, A2 is what mod 7?
A2 is. Oh yeah, what am I doing? A2 is 3, then 5, then 1, then 0, then -1, then -2.
26, which is 5. Or you can say -2. -2 to the fourth 16 minus 1 is 1. A5 is what?
A to the 5 is 0.
0. A6 is what?
-1, then -2.
A7 is minus. A8 is what?
A8 is, that's where I stopped. I thought.
A8 is what you said?
Wait, 1 second, let me just do it.
2, 5, 5. 3, 45, 42, 3, right?
Yeah.
A9 is what?
A9 is equal to, I think that's -1, 6.
6.
Could be wrong.
Let's check. Minus.
No, that doesn't make sense. It's probably not sense.
It's not -1. A9 is -1 or not?
I think so.
Okay, so why do you think so? Because look, 3 to the 9 minus 1, right? 3 to the 9 is 9 to the 4 times 3, right? 9 to the 4 is 2 to the 4 times 3. 2 to the 4 is 16. It's 2 times 3. It's 6 minus 1, 5. Or -2.
Yeah.
Understood?
Oh, it's -1. I forgot the minus. I did exactly what you did to get to 6.
Yes, at the end you should subtract 1. Okay, so now calculate A10.
A10. Oh, this is annoying stuff. It's 1.
It's 1. Okay, let's check. -2 to the 10 minus 1. So -2 to the 10 is 2 to the 10 is 8 cubed times 2.
Oh, no. Sorry, 0.
2 minus 1, 1. Yes, that's correct.
Oh, wait, no, yeah, I did do correct.
Okay, so we should keep writing to find, let me make it smaller. Find the pattern is what? So we calculated all the way to A10. A11 is what?
0.
A12 is what?
A12 is -1.
A13 is what?
-2.
It seems to have a pattern like this, but 2, 3 from 3, we have same thing. 3, -2, right? 1, 2, 3, 4, 5, 6. And this, right? So it seems that we have this pattern, so we should focus on these numbers, okay?
Yes.
Want more hint or that's enough?
I'll try.
Okay, sure. Want hint or want to keep trying?
Yeah, I'll take the hint.
Okay, what have you done?
I try to set it, try to like say, okay, it works every 6k minus 1 to go to the next 7 to the 7 to the k. Yeah, 7 to the k is a factor of a of 6k minus 1, and I try to go through the steps and show it, but I wasn't able to.
Yes, or we can 6k minus 1 or 6k plus 5. We want to focus on a6k plus 5. Now here we want to prove that because we have k, we want to prove it is multiple of 3k. Let's use m. We want to prove v7 of these should be at least what?
Greater than or equal to 0. 1, 1, 1.
K. Because it says it should be multiple of e to the k.
Yes.
Okay. Now we should say what? Okay.
Now we can say
so
that
v7. Now we can use. We want to use LT. A6m plus 5 is what?
Oh, LTE, yes. Because we know 6k plus 4 is gonna be always 1 mod.
Yes. Want to try LT on your own or one more hint?
No, yeah, I got it. Because you have that this is equal to v7 of a to the 6m plus 5 to the plus 4 to the 6m plus 5 minus 1 to the 6m plus 5. So this is equal to v7. We know a of 6m plus 4 equals 1 mod 7.
Yes, but let's do something before that. How can we prove first? We want to prove a6m plus 4 is congruent to 1 mod 5, right? Mod 7.
Yeah.
Try to prove this. We should prove it.
Okay. Yeah, I was able to prove it.
Can you explain?
Yeah. So what I did was, So I said that a of 6m plus 4 equals 1 mod 7. Then a of 6m plus 5 is 0 mod 7. A of 6m plus 6 equals minus 1 mod 7. A of 6m plus 7 equals minus 2 mod 7. Then I said, okay, a of 6m plus 8 equals minus 2.
Let me. You are trying to prove that a6m plus 4 is 1 mod 7.
Yeah.
And you want to use induction. You want to reach from 6m plus 4 to 6m plus 10.
Yes.
Okay. So let me write a6m plus 5 is what?
Is equal to 0 mod 7.
Yes, a6m plus 6 negative 1.
Minus 1 mod 7.
6m plus 7 is what?
Minus 2 mod 7.
Negative 2.
Yeah, minus 2 mod
7. 6m plus 8 is what?
3 mod 7.
How?
It's minus 2 to the power of 6 times n plus 1 times minus 2 to the power of 2 minus 1, which is equal to 4 minus 1 mod 7, which is equal to 3 mod 7.
Negative 2 to the 6 is what?
1 mod 7.
Is 1. Or from Fermat's theorem also we can
so
say.
it's minus 2 to the 6 times m plus 1.
Yes, it's 255.
No, but you can just do this as 2 squared minus 1, because this is 2 to the 6 times 2 squared, so I just say that.
Yes, we can use also that. Or 255, which is 45.
Yeah, then I do that same thing for all the other cases.
Exactly, like this one.
Sorry.
Look, this one also the power was 8, was 9, was 10, was 11, right? Or let me tell you something. Here, This power is 2, this is 3, this is 4 power.
Yeah.
5, 6, 7. And for 8, because look, when you raise something to the power of 8, for example, x to the power of 8. By Liddell-Fermat's theorem, we know that x to the 7 is what mod 7?
1.
No, x to the 7 is not 1. X to the 7 is what mod 7?
X to the 7 is equal to minus 1 mod 7. Yeah.
Is x. X to the p is always x mod p, okay?
Oh, okay.
So x to the 8 is x squared. So you can say it is again 2, 3, similarly 4, 5, 6, 7. Because the powers are same, again 2, 3, 4. We can say we have again same repetition, right? Okay, now that we know this, we can use LT, right?
Yes.
It's V7 of what?
V7 of so we just want to set 6m plus 4 plus 5 to the maximum possible to equal 7 to the k, and then we're done.
It is this one, minus 1 plus V7 of what?
Plus V7 of 6m plus 5.
Yes, and we know 7 doesn't divide a6m plus 4. 7 doesn't divide 1, but 7 divides a6m plus, right?
Yes.
Minus. Okay, then what?
Then we're done. Because we can just say that 6m plus 5.
We should prove it is at least k.
And you can just set 6m plus 5 to equal to 7 to the k.
Is it possible or not?
It is. Because you can just do 2 times 7 to the k or 3 times 7 to the k. So it's going to 100% be possible.
Look, maybe 7 to the k is not in this form. How can we say it has this form? Because you can say it's 1 mod 6, right?
Yeah, that's how you can multiply it by some numbers.
Yes, because 6m plus 7
it means 2 times 7 to the k.
Yes, or 6m plus 7 is these numbers are the numbers that mod 6 are 1, right? And because 7 to the k mod 6 is 1, so we can create, right?
Yeah.
Okay, or you can say m is, for example, 7k minus 7 over 6. We know it's mod plus 6, right?
Yes.
And for k at least 2. For k1 we know that, for example, this one works, a5. A5 works. Now we want to generalize this idea for general p. Okay? Now try to see, can you generalize this 7 for general odd number p, okay? Prime number p, try.
Yeah. You cut out at the end.
I said we prove for 7, right?
Yeah.
Now we want to generalize it and we want to prove it for general odd prime p, okay?
Okay.
Try to see, can you generalize? If you couldn't, let me know to give you hint, okay?
I think I have an idea. I think you can just say there's 2 cases for all p. Case 1 is it cycles between minus 1, 0, minus 1, 0, minus 1, 0, like that. Or in that case, it's easy to prove. Like, that's obvious because every single time you do that, the power will increase.
The idea, yes, exactly. The idea is similar, but you should reach a rigorous proof, okay? Yes, exactly. I think you are saying right. It is completely similar, but you should be able to reach a rigorous proof for all p's, okay? So try to see and
Can I have a hint?
Okay, sure. We found the idea in 5 and 7. We want to generalize it, okay? The first thing that we should try to find is to find the period, right?
Yeah.
Okay, can you say that the period is what?
The period is going to be, so in some cases, it's either going to be to the period, or the period is going to be equal to, what's it? Or the period is going to be equal to p minus 1.
Yes. So let's check. We know A1 is 2, right?
Yeah.
Here, and A2 is always 3, right?
Yeah.
A of which numbers are easy to calculate? Can you tell me, for example, A p minus 1 is what?
A p minus 1 is equal to, I don't know, what is it equal to?
You can calculate. You can say it is exactly what? Calculate AP minus 1.
Okay. Is it minus 1?
Why minus 1?
Because, I don't know exactly, it just sounds like shitty.
But can you tell me the formula of AP minus 1 is what?
AP minus 1 is equal to AP minus 2.
Yes.
Minus, to the power of, yeah.
The power of what?
P minus 1. P
Mm-hmm.
minus 1. Minus 1.
Yes. And it is equal to what mod P?
This is equal to, I don't know, this is 0. I don't know what this is equal to. 0 might be?
Exactly. It's 0, but or what? It has two cases. 0 or another number. Is it 0 or what?
I don't know. What?
Well, you
0
know,
minus 1.
let me, so, Little-Fermat's theorem. Little-Fermat's theorem says what? Says a to the p minus 1 is 1 mod p, right?
Yeah.
But it has a condition. That's the reason you don't know it. It is not always correct. What's the condition?
If a is equal to 0 mod p, then it's minus 1.
P shouldn't divide a, right? If a is multiple of p,
Yeah.
obviously it's 0. So it is 0 or negative 1. Negative 1 is for the case that p divides this, right?
Yes.
Otherwise, we have. Okay, so now we say ap minus 1 is 0. If ap minus 1 is negative 1, ap minus 2 is what in this case?
AP minus 2 is going to equal to 0.
Exactly. So we have these two cases so far, right?
Yes.
Now, ap would be what in this case? This case.
AP would be minus 1 and minus 2.
Exactly. Now, we want to say, okay, the period is what? So let's minimize these parts. Okay, if we consider, for example, AP plus 1, for this one, we can say it is what? This one is what? This one is what?
That one is equal to -2. Yeah. Oh no, 0, 0, 0.
0, exactly. AP plus 2 is what in this case?
-1. Those
Yes. AP plus 3, because it is again even, -1 to the even 1 minus 1, 0. So here we have this period. -1, 0, -1, 0, or 0, -1, 0, -1. And obviously we can prove it, right?
Yeah.
Okay, so it is case 1. It is case 2. Case 1 is easier. Try to prove case 1 first on your own, okay?
Yeah, case 1, I've done.
Okay, so can you explain for case 1?
You just call AP minus 1 equals 0
P to the k
mod
divides what?
A to the P minus 1.
E to the k divides AP minus 1?
Yeah.
It
And then you
cannot
say,
be correct.
okay.
Look, it cannot be correct because it is...
No. I'm saying A to the 0. This divides A to the P minus 1 plus 2k.
P to the k divides A what? Can you say it again?
A to the P minus 3 plus 2k.
A to the P minus 3 plus 2k. These plus 2k like this?
Yeah.
Okay, so let me check. Okay, let's see. How can you prove it?
Yeah, because we just say, okay. So we know A to the, when P is 1, A to the P minus 1 divides, that works.
Yes, AP
Then,
minus 1 works. Then what?
let me say, okay. A to the P.
Look, let me tell you something. It is not A to the... When you say A to the, it is power.
Yeah,
You should
I
say
mean
A4 because sometimes I think this. So then you want to prove AP minus 3 plus 2k plus 2. You want to use this 2k plus 1 to prove it is pk or 2k.
No, plus 2 times k, not to the power of k.
Oh, okay. So plus 2k.
Yeah.
So it is...
So it's the exact same things we did above for 3 and 5. It's the exact same solution.
Okay, so you say this one. If you want to prove, you can say on A...
We have to prove by induction.
P minus 3. Okay. So you can say that we know P to the k divides this. You want to use k to k plus 1. For example. Then you say, okay, AP minus 3 plus 2k plus 1 is equal to AP minus 3 plus 2k to the P minus 3 plus 2k plus 1 minus 1. And we know if we consider this one mod P to the k plus 1, it's -1, right?
Yes.
So AP minus 3 plus 2k plus 2 is congruent to -1 to the P minus 3 plus 2k plus 2 minus 1. Because it is even, this one also even, it's 1 minus 1, 0 mod P to the k plus 1. Yes, good job. Now we want to answer case 2.
Yeah, case 2 is the hard part.
Yes. Case 2 is similar to 7.
Oh no, case
right?
2 you just use lifting the exponents. So you're done.
Yes, exactly. It is similar to 7 and you should use lifting the exponent. Want to try case 2 on your own?
Wait, no, isn't it just that you have, you just need, whatchamacallit, you just need P plus 1. No, you need P minus 1 to be a power of, oh no, yeah, you need P minus 2 to be a power of, so you need, so, you're just done. You just do
Yes,
k times.
we should use exactly like 7, but it's important to be able to generalize it. Want to try to generalize it on your own?
We can just do it together.
Okay, so At first, we should prove the period is what?
Oh, I have to get a charger.
At first, we should prove the period is what?
I have to get a charger. 1 second.
You should. Oh, okay.
Sorry. Back.
No problem. So we want to prove case 2. We want to prove the period is what? Length of period.
Yeah, we want to prove that the period is p minus 1.
Yes, so we should try to find a of something. For example, look here. AP minus 1 was good because we could use Euler's Little-Fermat's theorem, right?
Yeah.
After that, it's good to find a what?
After that, it's good to find what do you mean? It's good to find a of 2p minus 2.
Yeah, a to p minus 2
2p
is
minus
what?
2. It can be minus 1.
Only minus 1?
Yeah.
Why only minus 1?
Because we can like discard when it's 0. That case.
No, maybe it's 0. We don't know.
No, but if it's 0, it just repeats. So we can
Yes,
discard
but
that case.
yes, but maybe it repeats from here.
Okay.
Okay, so in this case, a to p minus 3 is what?
Sorry? Oh,
Can we say this one is what or this one is what?
1.
Which question mark is what?
0,
First, second?
0 and 1. 0
Which
and
of?
1.
No. Only we
Top
can
is
say
0,
this
bottom
one
is
is 0. We don't know this one is what because it can be 1 to p minus
1 or minus 1.
No, not 1 or minus 1. 1 to p minus 1 can be any of them, okay?
Oh, okay.
Okay, now, so we have now 2 cases. Case 2-1, case 2-2. Okay, so let me minimize it. Okay, and this case is 0. Okay, so for this one, we raise to the power of p minus 1. For this one, we raise to the power of p. Can you tell me raise to the power of x to the power of p plus 1 for not only, for all x's from 0 to p minus 1? Is congruent to what mod A mod p?
It's compared to x squared mod p.
Exactly, because x to the p is congruent to x, okay?
Yeah.
Mod p. So instead of mod p here, you can say raise to the power of 1, right? Here, raise to the power of 2. Here, raise to the power of 3. Raise to the power of 4. Can you tell me this one is equivalent to raise to the power of what?
That. Well, what do you mean?
Look, for example, this one is what? Raise to the power of p plus 1. When you want to calculate a p plus 1, it is what? It is a p to the power of p plus 1 minus 1. But we said a p to p plus 1 is equivalent to a squared. So it is a p squared minus 1 mod p, right?
Yeah.
So for ap plus 1, we should raise to the power of p plus 1, but it is equivalent to 2. So we write to the power of 2 for this one, right? Understood or want me to explain?
Wait, can you repeat that?
Look, I said, you said. Do you agree for calculating AP plus 1, we should raise to the power of P plus 1?
Yes.
So you said P plus 1 is equivalent to a square. So I write this one is equivalent to finding the square of previous 1 minus 1, right? This one is raised to the power of what? AP plus 2. For calculating AP plus 2, we should raise to the power of what?
When calculating AP plus 2, you should raise to the power of
AP plus 2 is what? The formula of AP plus 2 is what?
AP plus 1 to the power of P plus 2 minus 1.
Yes, you said power of P plus 2 minus 1. But instead of P plus 2, we can write what?
Instead of P plus 2, we can write I don't know, what can we
Look, instead of P plus 1, you said a squared. Why you said a squared here?
So we can write x cubed.
Yeah, so here we should place cube, right? Because the P is 1.
Yeah.
So I can say instead of when you want to we want to only calculate mod P. So instead of raising to the power of P plus 2, you can raise to the power of 3.
Okay.
We are writing all these numbers to prove the period, okay? To say, okay, all of them are equivalent to 1, 2, 3, something like that. Okay?
Okay.
So can you tell me now, question mark is what? Here we should raise to the power of what? It is equivalent to raise to the power of what? 2p minus 3.
It's equivalent to raise to the power of, I don't know what, raise to the power of what?
So try. Look, when you said 1, 2, 3, it is only the pattern and you can easily find this. It is not something hard. Try to figure it out.
I don't know.
So let's try. X to the 2p minus 3. If you use x to the p is x, it is what mod p? Can you tell me if x to the p times x to the what first? 2p minus 3 is x to the p times x to the what?
P minus 3.
P minus 3. X to the p is what mod x? Mod p?
X.
X. So x times x to the p minus 3 is equal to x to the what?
P minus 2.
Finished. So 2p minus 3 is equivalent to p minus 2, right?
Okay.
Next one is equivalent to the power of what?
Next one's going to be equivalent to the power of P minus 3. P minus 1. P minus 1.
Exactly. Now let's calculate next one. A 2p minus 3 is equivalent to the power of what?
P.
But instead of to the power of p, you can write to the power of what?
Yeah.
Instead of p, power of what?
X.
Yes, x to the power of 1, right?
Yeah.
Okay. Now it seems that we want to prove the periodicities, right? So when it is -1, the next one is what?
When it's -1, the next one is equal to -2. Yeah.
Exactly. And so if it is 0, the next one is what?
0 next one is -1.
Exactly. Okay, so this one is -1. Now if I consider a 2p minus, why I said 2p minus 3? 2p minus 1. Then 2p, this is raised to the power of 2, right? So for this one, when it is -1, this one will be what?
That's to the power of -1. That one is going to be 0 again.
Yeah. So again, do you agree we have 0, -1, 0, -1?
Yeah, it's the same case as number 1.
Yes. So by the same way, we can prove.
Yeah.
Now we should focus on this. Do you agree here we have same repetition because look again we have power of 2, power of 3 to power of p minus 1.
Yeah.
And look, when this one is -2 and the power is same, -2, the power is same, so the next number will be same as this one, right?
Yes.
Okay, so we proved here the period is p minus 1, right?
Yes.
And can you tell me the form of the numbers that are multiple of p are what? What numbers?
A of, wait 1 second. P minus K times P minus 1 minus 2. Minus 1.
Exactly. Or let's write m times p minus 1 because it is k
Okay.
to
Yeah.
find n. Okay, now you should prove why there exists a good m that p to the k divides this. You want more hint or that's enough?
No, can't we just do this? Like, isn't this the exact same thing we did above? We've
I want to
shown
do it
that
together.
it's always been 1 mod before. So we can just use lifting exponents. Now we just need to show that.
Okay, now because we proved this one, we know previous to this. We should prove previous one is what? To use LTE is 1. So how can we prove previous one is 1?
We can do that by...
Look, we know a2p minus 3 is 0, right?
Yeah.
Or for example, a2p minus 3 is 0 mod. Now, what can we say about previous one? 2p minus 4 can be what numbers?
2p minus 4 can be any numbers.
No, not any numbers.
Oh no, just 1. 1 or minus 1.
Yes.
Just 1, no, just 1. Minus 1 is not a case, so just 1.
Let's check. Because 2p minus 3 is odd, right?
Yeah.
But in general, if you want to consider previous term of this one, so we know what? We know p divides a sub m p minus 1 minus 1. And we know it is a m p minus 1 minus 1 to the m minus 2 m p minus 1 minus 1, right?
Yeah.
And it's 0 mod p. So what can we say? We said this one is 1 or negative 1, right? It depends on the power that it's odd. Because we know power is odd, right?
We know it has to be 1.
So why it has to be 1?
Because if it's negative 1, then it's going to be negative 2 in the second thing.
But maybe, for example, 2 to the power of this will be 1 mod.
Oh, yes.
So try to prove it has to be 1.
I don't know, can I have a hint?
Okay. So here, look, I want to use this one. At first, I want to prove this one is not 0. Obviously, it's not 0, because if it is 0, 0 minus 1, it's negative 1 is not 0, right?
Yes.
So, because it is not 0, you can raise to the power of p minus 1, which is 1, right?
Yeah.
But we have one problem, it's negative 1. So I prefer to write it as something plus something. So instead of minus 1, we can write it as mp minus 1 plus what?
P minus 1 plus p. Plus p minus 2.
Plus p minus 2, right?
Yes.
Okay. So I write this one. Let me correct this. Plus p minus 2, then this one is plus p minus 3. This one p minus 2, right?
Yes.
Okay. Now we know it's so. Here I can write it as what? I can write it as a to the mp minus 1 plus p minus 3 to the power of p minus 1 to the power of m times a sub mp minus 1 plus p minus 3 to the power of p minus 2, right?
Yes.
Okay, so if you consider this one mod p, this one is what?
This one is...
Let's call this number. Let me call y is a m p minus 1 p minus 3. it would be easier to work with. It would be y to the p minus 1 to the m times y to the p minus 2. So y to the p minus 1 is what?
Y to the p minus 1 is equal to just 1 mod p.
Yes, so it would be equal to what? The whole thing.
Just y to the p minus 2.
Mm-hmm. And now I want to calculate this. I know that y to the this is 1. It is equivalent to 1, right? Because if you take negative 1 to right side, it's 1. Now, if I multiply both sides by by y to the p minus 1 is if I multiply both sides by y to the p minus 1 is congruent to what mod p?
Y mod p.
Y. I multiply by p. Now, y to the p minus 1 is what? Mod p.
1 mod p.
So we prove that y is 1 mod.
Oh, okay.
Okay, now y is 1. So, if we want to use LT, it is possible, right? Because when we want to say, we say, okay, VP
now it's just simple LT.
Exactly, plus p minus 2 VP of A M p minus, or you can say y to the m p minus 1 plus p minus 2 minus 1. Then it would be VP of y, and we know that p divides y minus 1, p doesn't divide y, p doesn't divide 1, p is odd prime, so it satisfies all conditions. So VP of y minus 1 plus p of m times p minus 1 plus p minus, right? We want that this part be at least what?
You want that part to be at least k.
K. So you should prove there exists a good m that, for example, this one
satisfies this.
Yes, so p to the k, we want that p to the k divides mp minus 1 plus p minus 2. So you should prove there exists a good m.
Yeah.
Okay, so try to prove it.
No, but there obviously does exist a good m. Because p minus 1, like you can just multiply p to the power of k by like any number. You just need it to be equal to 1 mod p minus 1.
Yeah, so.
Or minus 1 mod p minus 1.
mp minus 1 plus p minus 2 should be equal to p to the kt. M should be equal to p to the kt minus p minus 2 over p minus 1. So this one should be multiplied p minus 1, right?
Yeah, but this is the same as just saying p to the k times t plus 1.
Mod p minus 1
p
is
minus
what?
1. P minus 2 is just p minus 1 minus 1. So it's just p to the k plus t, p to the k times t plus 1.
It is t plus 1, right? Agreed?
Yeah.
So this one should be 0. So you can say t is t minus 2, for example.
Yes, and that works. Then hence
if we plug in this, m is p minus 2 times p to the k minus 1 over p minus 2. This one divides this, and we found a good m. Okay.